Hi, everybody. Welcome to the PLI talk on 26th of September, which happens to the Thursday, as we know. Today, we have two amazing talks lined up for you. One by Yong, he recently joined Princeton as a postdoc, and by our very own Colin Wang. We also have a lightning talk by Seth at the end of the presentation. So let's start with Yong Lin. So Yong Lin is currently a postdoc co-hosted by PLI and Chu Jin, and he obtained his PhD degree from the Hong Kong University of Science and Technology. He has also won the Outstanding Paper Award at NACL this year, and he is an Apple PhD AIML Fellow. Give it away for Yong Lin.
Hi, everyone. It's a great honor here to introduce our recent paper. And I'm also very interested in a discussion on how you visualize this topic. And before introducing our work, and I think I'd better to introduce myself on my earlier research. So many of my research on language models focused on their post-training of language models. Suppose we have a pre-training language model, it could be unhelpful, just not following your instructions, and it could make up facts like hallucinations. It also contains bias and toxic content. So we need to tune the language model further to make it helpful and honest. My research objective is to develop effective ways to improve language models' reliability and capability in terms of these attributes we want. And also, I want to provide in-depth empirical and theoretical understandings in the behaviors and some phenomena, mostly from the machine learning part. So let's revisit the current pipeline, popular post-training pipeline. First, when we get a pre-trained language model, we will collect the instruction tuning dataset with the prompt and the answer, and we fine-tune the language model on this set to let it get the style of the conversation. Like you ask it a question, it knows you need to respond instead of repeating your question. So after this stage, the language model somehow understands the format of the conversation. And then in the ILCF stage, we further collect pairwise data. One is given a prompt. We collect the two responses typically, and we ask human to annotate which one is better. And so we have a pairwise responses, and we will use this pairwise data to further improve the language models for better alignment. My main research also focuses on this pipeline. In the first stage, we identify a problem on the existing instruction tuning pipeline. That is, instruction tuning forces the language model to answer a question, even the language model does not know the answer. So in order to match this instrument, it might make up something to just match the style. So that's what we usually call hallucination. In this work, we design some methods like to instruct language model to respond I don't know to the questions it does not know the answer. And otherwise, he will respond as normally. I will not discuss this project detailedly. And another problem is what I'm thinking for a long time. That when I first came across this pipeline, I'm thinking why we need two stages, like why IO, we should further use the IO based on SFT model. Why just we keep SFT or something like that? So this is the main focus of this topic, this talk. And a follow-up work on the IO stage is to solve a problem called reward misspecification. That is, typically we use a single IO model to aggregate the preference of everyone, right? So suppose the majority might prefer some more detailed answers, but some minority might prefer the concise answers. if we aggregate the preference of everyone, the reward model will prefer the preference of the majority, just ignore the minority. So we can, they can imagine that sometimes you wanted to produce some concise output, it cannot do that.
Is that actually true? Like if it's 60-40 split, I don't think it'll go with the majority. It'll probably just do both.
Sorry.
I mean, it's probably not true that if there's like a 60-40 split in preferences, it'll go with the 60%. It's not true, right?
Yeah, it depends how the minority group is, how large it is. If it
Right.
only 10%, it probably be the case.
Not sure if 10 is already big enough to have some effect.
And also, after several stages of fine-tuning, we observe that the performance of the fine-tuning model may degenerate on some abilities the precision model already acquired. So we also studied how to eliminate the pattern. In this talk, I will mainly discuss why we need RL, and let's first look at several ways to align the language model. First is SFT. Yeah, it is straightforward. Just we collect the good answers and maximize the log likelihood of the good answers. It's straightforward. And the other is DPO. DPO, we collect pairwise data and use to maximize the difference between the chosen answer and the rejected answer. By this means we want the language model to distinguish between the good and the bad answers. So we can imagine that DPO is better than SFT. It's not too hard to understand since DPO utilize both the positive and negative samples. One confusing between DPO and RL is not so clear so far is that whether we need RL compared with DPO. They are from the mathematical side, they are somewhat equivalent if we have large functions class and infinite samples. Like we have a lot of training samples, they are equivalent to the limit. RL first fits a reward model on this distinguish between chosen and rejected answers, and then we maximize the reward given by the reward model through RL algorithm like DPO or the DPO or rejection sampling like that. So we would like to understand the difference between these two. Okay. So the question to make sure we are all on the same page, I want to highlight our question. The question here is that if we collect the preference data set, if we face a new scenario where we can find a preference data set, which is better way to align LLM? Do we need to use DPO or other preference learning method? Or we should first train a reward model and then do something later? This DPO claims they can bypass the reward model, right? So, and also, based on our findings, we want to improve the current practice. Let's first look at some basics. In RL, we first fit a reward model, and they want to maximize this the policy in terms of the expected reward. And we can, if the reward model is given, the optimal policy to solve this question is solve this problem is just we can write it explicitly. We can ignore the normalization part and also the reference policy. We can see that the reward model directly corresponds to an policy. So if we have the underlying golden reward model that which driven the preference of human, we will have the optimal policy. Yeah. And as for DPO, it bypass the reward model by reparameterize it through a preference model over the reference model. They are in mathematical, they are equivalent. And yeah, they have shown this, and they call this reparameterization as the implicit real model. So they have shown some equivalence between the implicit real model as the explicit real model. And what we want to show, to investigate here is what does the implicit real model actually do? Does it do as well as the explicit real model, or does it not? Why we care about this question? This is we can say if DPO's implicit real model is good, like it does as well as the explicitly fit real model, it means that the policy itself is already good. We do not need to bother at all on other improvement for DPO. Otherwise, the DPO's policy is suboptimal. We need to do some effort, and then we still have room for improving the DPO. Here, by DPO, I mean may include other practice learning models method. Okay. So let's just suppose we have a data set. We can fit a DPO model. And here is our implicit real model. And then we can measure the accuracy of the implicit real model on the testing data set. And also, we can also fit explicit real model on the same data and test it on the test data. So we are curious about the test performance of two real models. One is implicit from DPO, the other is explicit model. And we collect a lot of data sets with a lot of settings and very as much as we can. And we have 3 models, 5 settings, and each settings we use 5 seeds, and then we sweep over the hyperparameters. More for DPO, since DPO have an additional hyperparameter. Okay, let's see the results.
No, sorry, what the shift can you just go back to the slide? I'm just looking at the last column.
Oh, okay. Okay, I can explain a bit. Yeah. The prompt shift is that in the test we have different prompt, and the response shift is in the test that the prompt is from same distribution, but the response is drawn by another model. Yeah. We directed a lot of experiments in one setting, and we can see that the red bar is the explicit real model, and the yellow bar is the DPO. Oh, sorry. The red bar is the DPO, and the yellow bar is the explicit real model. We can see in almost, except for this case, in the rest of the settings, the real model, explicit real model, outperform the DPO's implicit real model by a significant margin, especially when there is a distribution shift. And we all know one aligned model can encounter out of distribution prompts or responses in when it is applied into application. Okay, so this is the what is the real world model's performance in terms of DPO's implicit real model and the explicit real model.
Question. So this is about OOD resilience of the supervised training, right?
OOD, yeah.
Performance of supervised training.
Yes.
Are there other studies which have also looked at OOD performance of supervised training, not just reward, but like any?
Yeah. There's one. I remember one literature that compared SFT with IL in terms of the final policy.
In terms of OOD.
In OOD setting, yeah. So let's see the implication of this result. First, we have the reference. Suppose the reference policy is here, and the optimal policy is there, and we know that the DPO is not optimal. Okay, since DPO's implicit real model is already inferior to the real world model we fit on the same data set, and the explicit real model's policy will be here between DPO and the high star. So that means we still have room to improve for among here, and we will introduce it later. And let's first put this question aside, and let's first investigate why DPO is inferior to an explicit rule model. Yeah, let's look, find some intuitive explanations. If we imagine that which task is more difficult, if I ask you to cook a delicious dish, or ask you to tell whether a dish is delicious or not, I think most people will agree that it is quite easy to tell it is delicious or not than cooking a delicious dish. So the first one is more like a generation task, right? The second one is a discrimination task. So for DPO, we somewhat like it directly to generate good answers. And for real model, we just ask it to differentiate between good and bad answer. So that's intuitive why a real model would be easier to train. And let's see some qualitative experiments. So we ask the language ChatGPT to complete to respond to some very simple instruction following tasks from if evolve, like please response with at least 25 sentences. Please avoid use the letter I more than twice. So we can generate the response by ChatGPT and verify the response by the rules. And we can also ask the ChatGPT to check whether its own response matches the rules or not, and compare with the ground truth.
But can GPT-4 evaluate the example too? The R's in strawberry it can't do, right?
Sorry? No, you mean GPT-4 cannot do this?
Evaluate, no, or even evaluate, well, the solution to example 2.
Example 2? Oh.
I mean, you know about the R's in the strawberry, right?
Okay. But I think GPT can evaluate since it responds if there is more character more than 2 characters I. Do you mean GPT-2 cannot?
You're clearly not on Twitter because like that's like a meme, strawberry.
I see. But as far as we asked, we found that ChatGPT can judge like with 80% accuracy, but its generation only match the 50% accuracy in terms of this.
That's probably true.
Yeah, not specific to this question, but a lot of questions. Okay.
But this doesn't mean much, right? I mean, this formatting things are very, very hard for autoregressive model.
Yeah.
So that's not a very good
Okay.
test.
Okay.
Yeah, so I have a question about so we all agree the generation task is harder, but why did it choose a model that finally performs some other downstream tasks?
Very excellent question. I will expose this problem in the next slide. Thank you for the question. So yeah, so why a harder task will lead to worse generalization? And let's look at in another perspective. So suppose we have a base model, and we fine-tuned it to obtain a DPO model. Suppose the task is very hard. We need to tune the base model very hard to satisfy the loss or like solve the task. So we can imagine the parameters in the neural network will change a lot. That could possibly result in a larger distance between the DPO's parameter after fine-tuning versus the pre-training checkpoint.
Yong, you have 5 minutes left.
Okay, I will speed up. So we can also measure the distance for the reward model versus the pre-trained model. Let's ignore the linear head first. And then we will, here is the results. The reward model, here is the training accuracy, and here is the validation accuracy. And then we can see when achieving the same level of training accuracy, the reward model's distance moved is much shorter than the DPO's distance moved. We can imagine.
Which is shorter again?
I visualize the parameter after fine tuning versus the per-tuning parameter to visualize how far the parameter traveled in the parameter space.
Those are two different tasks, reward model and DPO. So
Yeah.
that's
They are two tasks.
what
I
is
agree.
DPO is like full training of DPO,
Yeah, the real model is also for training.
but on a very different task.
Yeah. So to solve the DPO loss, the algorithm needs to find the solution in a very long distance. It looks for the solution in a lot of functions, and in the real model, it looks the solution in a smaller space, since it just move a little bit distance. So but it is a roughly explanation, not a very rigorous theory. So recall the generalization gap. It determines on how much functions you look for the solution in the training set. So I mean, DPO looks for the best solution in a lot of functions and then moves much far away. And reward model located in a relatively small function space. This is some intuitive explanations.
And two different tasks, therefore you can't complain. You can't compare them.
I agree with that.
So that's a Rademacher complexity. So isn't it a pretty loose bound?
It is just for illustration,
Okay.
not for rigorous theoretical claims. So let's go back to what's the implication and what we can do based on this result. We now have the DPO policy. We know it is in this area, and we can do better if we optimize over the real model. So there is some way we can improve DPO's policy towards a better policy. So suppose we have the same data set and we train a DPO, and we have a DPO policy model, and we also train a real model. They are all on the same data set. And then we sample a lot of response for the DPO policy based on for the same prompt set. And then we use the reward model to rank the response according to the reward given by this reward model. So we can construct pairwise data by what the reward model tells. And then we add the pairwise data back to the DPO pipeline. We can iterative between this procedure. Okay. We train it on the archer feedback, and we use the Gemma 2B instruction tuning checkpoint, and then we evaluate on the alpha evolve with a win rate over 54. So the base model is about 8%, and if we conduct DPO, it is about 10.
You have 1 more minute.
Okay, wait, I'm just finished. If we iterate for one iteration, we will have much better, and the second iteration is also better. So the improvement is like boosted from 4 to about 8. Not a trivial improvement. So the takeaway is that when you have a collected data set, you should not expect your direct preference learning model method could do well, and you should train a real model and use some kind of iterative method. And if we have off-the-shelf real models, just use them, and they can save a lot of time. That's all. Yeah, thanks.
Thank you, Yong. We can take questions now.
If you have a reward model, like why don't you just use PPO?
Do you mean the difference between PPO and DPO?
The difference between PPO and like the iterative DPO with the reward model.
So sorry, I didn't Okay, that's my question.
But just like if you have a reward model, like it's the iterative PPO better than like just using PPO.
Yeah, it's a good question. So far, I don't have the answer, and I think it is also very popular question. Someone must be working on this.
Randomly skip
That's fine. Yeah, question too.
Oh, click the. And you can do the present. Oh, you just use view on this one and.
There's a new entity called AI administrator. Yeah, we will launch it.
Yeah.
That'll be easier for me.
This one is always.
Yeah, okay, that's good, that's all I need. It is,
And then even CSML, we use their administrator left hand. No.
Yeah, they should.
Oh, good.
Because how
Yeah.
much cheaper?
Good.
CSML is not
All right, everybody, our second speaker today is Dure Colin Wan. You can just call him Colin. And he will present charting graphs in realistic chart understanding in multimodal LLMs. So Colin is a second year master's student advised by Dante, and he earned his Bachelor of Science in Data Science and a Bachelor of Arts in Cognitive Science from UCSD, and he's also a 2025 Siebel Scholar. Please give it away for Colin.
Yes, you didn't do the second part, but anyways, hey everyone, my name is Zuri Colin Wan. Today, I will be introducing you our latest not preprint. Actually, it was just accepted this morning in yours. So it's in yours. Okay, charting gaps in realistic chart understanding in multimodal large language models. We have 11 authors from the PLI. And then we have one author from University of Wisconsin-Madison, who is actually the first author of Lava. And we also have one, I think it's an exchange student in our PI, who's from the University of Hong Kong. So multimodal large language models are very hot nowadays, and almost all the models have to evaluate on some chart understanding evaluations before they actually get to meet the public. When Cloud 3.5 Sonnet was released, it was actually tested on 5 multimodal benchmarks, so 2 of which like are heavily based on chart understanding. So one of it is chart QA, with exclusively chart question answering, and the other one is MathVista, where more than 20% of the samples are about like understanding the charts. So given its performance over 90% on chart QA and 68% on MathVista, can we really say that they understand charts? In the next section, I will prove you that these numbers represent an over-optimistic measure of progress. So I will start with the claim. Existing benchmarks, they oversimplify chart understanding. As background check, MathVista is a multimodal math reasoning evaluation suite. 20% of the samples came from those benchmarks, DVQA, Clock QA, Figure QA, and Chart QA. This evaluation suite gets very popular recently, and Chart QA is often used as a standalone benchmark to test chart understanding. But if you look at the chart sample, they're either synthetically or picked up from a single source of like basically homogeneous charts you see. So DVQA is fully synthetic. All of them are just bar charts. Plot QA very simple. Figure QA is also very simple. The styles are even very similar. And chart QA is just picked from several websites that all use the same style. So let's begin with a fact. At least a fact in open source, multimodal large language models. So they are often trained on existing chart datasets. And that means that all the previous datasets, such as Figure QA, DVQA, Plot QA, Chart QA, they are part of the instruction tuning dataset to train these models. And while they do not use the test set to train it, which is otherwise obviously wrong, they actually probably did not realize that the synthetic nature of this dataset, where in-domain training can lead to significant boost on in-domain evaluation. But what if samples no longer look like what's being trained on? That's actually the motivation of chart type. So from that point, we actually started viewing 2 sets of chart question answering samples from 184 existing chart QA samples in MathVista across Figure QA, DVQA, Chart QA. So in short, we have a modified chart set where we keep all the questions in 184 samples the same. Okay, so it cannot be exactly the same, but it's essentially the same type of questions. For example, if the original question asks if something is greater than something, then we also ask the same question. And now we also collect charts from archive papers that can be asked with the same type of questions. So basically now we have this kind of, modified question, modified chart set. Okay. And then in the modified question set, we basically modify the questions and keep the charts untouched. Note that there are different questions, but they're still contextualized within the charts. And in both settings, we ensure an equal amount of yes/no answers as well as third number answers. And all the samples in the two sets are annotated by ourselves. Human annotated. And once we have the modified chart set and modified question set, we compare the performance change when models are evaluated on this set with respect to the original sets. And here is what we found. Okay, so we selected a range of open source models where they stated that these models are basically trained on the training set of existing chart understanding datasets. And we compare their performance with proprietary models. And as you can see from the charts, all four proprietary models, I believe it's Cloud 3 Opus, Recard 4, GB4B, and GB40. They closely stay along the diagonal line, meaning that they're just probably fine, right? They get a similar performance across modified questions, original questions, modified charts, and original charts. But if you look at the open source models, they all get exploded. We have seen the most extreme case happening to the Sphinx V2 model. The accuracy just dropped from 60-ish to less than 30, once only the questions are changed. Similar but less severe patterns are observed in all the open source models. This basically demonstrates that in-domain evaluation leads to an over-optimistic measure of progress, and it sparks us to propose the CharCat benchmark, which actually aims to fix this in-domain evaluation problem. So as a wrap up from the last section and the introduction to this section, CharCat represents the first realistic, diverse, and challenging chart understanding benchmark. That being said, all the charts and questions are made by people from the real world. And because they're made by different people, the charts are naturally diverse, and so as the questions. And finally, all the charts are collected from recent papers from arXiv, which means that the charts themselves are usually, for recent papers and just naturally challenging, right? And with challenging charts, we naturally ask challenging questions. And know that all the questions are labeled with our in-house labelers, which are just mostly graduate students from Princeton. Instead, we didn't hire any Turkers because we don't really trust them nowadays. So let's unfold the chart type and begin now, like how we handcraft and handpick the charts. So for this, we actually decompose into 4 steps. In the first step, we perform like data pre-processing, where you bulk download hundreds of millions of archive source files from archive's establishment. And in the end, we decided to only go with the figures from 2020 to 2023, as we found the charts from like earlier years, they're not as visually diverse as in more recent years. So we include all the subjects that are from arXiv, which are statistics, quantitative finance, biology, physics, mathematics, etc., etc. For all the figures within this years and subject, we use LaTeX parsers. Monjo wrote that part, and we actually found out all the figures used in the paper, and then we re-render those vector-based vectors such as PDF and EPS. We re-render them into high-resolution standard JPEG files. We resize them to have a longer set of 1024 and padding the rest, white color. We choose this resolution because lots of the charts from arXiv, they contain subplots and charts that can be unreadable if it's rendered in a resolution such as like 336. That's usually the standard resolution for VLT models. For all the JPEG we render, we use a SIGLIT model to do semantic pre-filtering. For those who don't know what the model is, you can think of it as one capable of finding semantically similar figures from an anchor set of figures. So you use this kind of anchor figures, and you can use this SIGLIT model as a filter to select figures or charts, right? So here we simply use the chart samples in MATLISTA as the anchor set of figures. We take the average image embedding of this chart and keep all the figures from our render archive images with a confidence interval of 0.65. And this number is important, neither too high or too low. Because if you set it too high, say 0.8, all the charts that are selected looks very similar to what we've seen in MATLISTA. And if you set it too low, it's likely that it just not do any pre-filtering at all.
So you basically bring
Yes.
area based on the LaTeX leggings for the charts that you extracted.
No. So they usually attach their PDF files and EPS files for charts because usually you use those files to use a matplotlib to generate those figures. Yeah. We actually use a renderer to convert those vector-based PDF files, PDF-based figures, to the JPEG file raster.
Oh, I see. So you take the PDF directly. You don't really.
We take the PDF version of the figure. Yeah, and we render it into JPEG.
So yeah, I can see that not having a high failure rate because if you recompile from LaTeX.
Yeah, if you recompile, I think it's more.
Might be a bias.
Yes. So after pre-filtering, we sample 750 figures from each and subject. We actually start involving human intelligence, and we ask the annotator to choose the best part from a set of 10 figures at a time. So this is actually an example in our annotation. So we ask the annotator to prioritize the clarity and diversity of the chart. That's the first priority, okay? So after step 3, we ensure that each year and subject contain roughly the same number of charts, which is like 75. And at this point, we'll perform the final data processing where we apply a model-based approach. So we deduplicate charts based on greater than or equal to 0.95 of pairwise coefficient similarity from single image features. Sometimes we realize that, in the same paper, you can have like 2 figures that look really similar there, just like for different experiments, right? So we basically did some semantic-based deduplications, and finally we did a full pass of human inspection to catch any non-charts and blurry charts that were accidentally selected by the chart selection annotator. And after this step, we ended up having 23 charts. It's a weird number, but it's fine because I graduated in 2023 from my undergrad, so I use the 23. Now for each chart, we pair it with discrete questions. We actually realized that no matter how visually diverse the charts are, they just share common elements. And you can ask the same question to many different charts with no compatibility issues at all. And to this end, we inspected a lot of them and come up with 19 unique questions. I want to say a kudos to Lucy, who helped a lot on thinking of like what are the unique elements are. They basically cover all the properties of the charts. For example, the title, x-axis label, y-axis label, text. These are some basic information that we want to ensure that the model learns some basic enumeration and comparisons. We also have questions like, the max value and the range of the continuous legend or consecutive differences between the text, or enumerate all the discrete labels. After that, there are more complicated but basic questions in patterns, such as line intersection, trend of data, as well as subplot layouts, which we term as pattern recognition. And finally, we have like counting, where we ask model to count at different granularities from labels to lines to subplots. Oh, and for compositionality, we ask the model to count the tick labels across axis. And it turns out that this question is very important as part of our analysis. So stay tuned. I will talk about this later. Concretely, I will show you one contextualized discrete question. For example, for this, we ask the subplot at row 1, column 5. This one, right? Which is obviously the top right one. Well, what is the rightmost label take on the x-axis? I think from a human perspective, it's a bit small, but from a human perspective, it's concept. But all the models basically said like strap concept. I think they realized that they probably merged these 2 labels together, but in fact, it's just poorly designed. They belong to different bars. Models think that they're just from the same labels, the same single unit of label. So now this model can get it right, even including GB40. So I mean, like even in this very simple diagnostic questions, the strongest model can still make very stupid simple mistakes.
Sorry, what changed? I didn't quite get it.
This one? Oh, sorry, it's a bit small.
Oh, I see. The top answer is
close
correct.
to each other. Yes.
The top answer is correct.
Oh, none of the answers are correct.
Sorry, all of them are correct.
All of them are wrong.
Is it possible I can render you?
I see. Row 1 and column 5. Got it. Okay.
Yeah, it targets this chart, but it thinks that this belongs to the same label. Okay, so they actually belong to different bars, but they're just the tags are very close to each other, and they think that they belong to this bar.
Is it possible rendering?
It's not rendering. I mean, it could be the author, like the author who make the plot issue, but I think in terms of render, we have the high resolution, and if humans can know that they're from different labels, I think the model shouldn't make the same mistake. Yeah. And one more characteristic I want to show is that we have like intentionally 25% of the questions that are unanswerable, such as asking the number of lines in a bar chart. Maybe you can say that this bar is a line, but I don't really think so. Know that we have like proper instructions to the model to say not applicable for unanswerable cases. Usually you would just say not applicable to a bar chart if it contains any lines. But yeah, in 4 out of 6 models shown here, they all pretend that there are some lines in this plot, in this bar plot, which kind of makes sense. Yeah.
Yeah, it kind of makes sense.
But seriously, there's no line on the chart based on the definition because it's a bar chart, right? So GB4 answer not applicable, but some models just say the plot contains 4 lines. I don't know what the 4 lines are. Maybe it's referring to the legend. But obviously, I don't think
So-
it's yes.
But this question is ambiguous. Like lines means what? What does line mean in the context of plot? I see plenty of lines. Straight lines.
There are some follow-up instructions, like if you don't see clearly, like clear lines from a chart perspective, like chart data.
Yeah, so that's what I'm
you should
saying.
answer not applicable.
Yeah,
So there are still models saying not applicable, but lots of models just say, like give you some numbers like 4 or 10 or something.
but was this automatically generated? Is this one of your things?
This
Like,
is one of the template-based questions because
Nice.
they're applied to different charts. So now after this more complicated descriptive questions, we also construct reasoning questions to truly challenge these models. So if you consider reasoning questions as challenges to these models, the descriptive questions are just really easy. The core principle of reasoning question is that each chart represents a unique story as a standalone set. So we have to hand draft each individual question tailored to the content of the chart. And we actually do it without access to any of the captions or paragraph that it originally accompanies. That way we prevents from any data leakage, right? And to do this, we start from a source chart, and then we give this chart to the GPT-4V model to generate some sample QAs following a predefined instructions. And from there, we release the source chart and all the sample QAs to our excellent graduate student annotators. And now they face 4 options. It's possible that one of the QAs are really good. The answer is accidentally correct. GPT-4 made a lot of mistakes. In which case, they just put it as a final QA. In some cases, annotator find a really good questions with the wrong answer, and this results in a multiplication of the answer with the same question. Sometimes, like if you can find good question and good or bad answer, this only account for like 20% of the QA sources. Another 20% of QA sources happen when the annotator thinks that a question is interesting only if it's asking for some other potentially more challenging variables. In which case, they just multiply both the question and answer. And in the remaining 60% of the time, the annotator believes that the GPT did a very, very bad job and end up writing their own questions and answers. So for each answer that annotator crafted, they need to ensure that the answer are in 4 types: text in chart, text in general, number in chart, and number in general, which we'll discuss what concretely mean. Basically, text in chart means that it's kind of piece of text that are from the chart itself, like what is the label of the y-axis in the subplot, and there are a lot of conditions. Where the blue dots form the smallest clusters. So you need to figure out that it's this subplot, and then you need to figure out where is the y, it's here. Okay, so it looks blurry here, but I can guarantee that if you see the actual figure, it looks very clear to humans. Text in general mostly asks for trends, like whether it's increase or decrease, but this one is a bit tricky, running to the nearest hundreds. What is the first frequency where the theory curve achieves approximately the same Raman intensity as the value achieved by the experiment curve at this? A lot of models make mistakes. I think this question was annotated by Alexi, was graduated from our postdoc program. Number in chart. How many false negative detections are there for this in the X dark data?
How do you evaluate the correctness of the answer?
Okay, we have the number in chart and number in general. Those are like you need to ground number in the existing in the chart, or just like number in chart is mostly counting. Next slide. Now let's talk about how the responses are writing. So because chart type sources charts from like scientific domains, sometimes like a lot of charts contain equations and math symbols, and some models like to give like UTF alpha character, and some models just give LaTeX grammar to represent it. And this means that we can't usually do exact match. But we talk about the fact that we have specified a fixed type of answers, and we actually make all the answers easily verifiable via LMs, where we actually design in-context learning examples and grading instructions for each answer type. And then during the response grading, we just retrieve the relevant ICL examples, in-context learning examples, and instructions along with the question. This is pretty similar to MathVista, where we provide with the reference answer provided human and the model's response, and we ask GPT-4 to basically assign a binary score, whether it's correct or not correct. We don't offer partial parameters because many recent work indicated that such design can cause evaluation to go beyond the factuality. Sometimes maybe the style matters. Sometimes maybe other things we don't know that matter, right? So there's an interesting point where one of our reviewers suggested us doing a manual evaluation on this automatic evaluation because concern maybe GPT-4 is not 100% correct. And our result actually shows that they match 98.5% of the time, which is quite high. And the F1 score on matches.
You have 5 minutes.
Yeah, that's okay.
Are you worried about any leakage? Like someone could try to reproduce this pipeline and generate the answers themselves and kind of like game the benchmark? Like, are you worried about that leakage?
What kind of leakage?
Like, I've seen someone could generate the answers, like the correct answers using exactly the pipeline that you described.
Yes, but if they get a very high and potentially suspicious score, I guess someone will want to reproduce it with their models. I guess it's fine, right? Okay. As of now, Shark have evaluated more than 40 multimodal large language models internally evaluated by companies. They're also currently internally evaluated by companies developing proprietary models. I won't say which companies, but I guess we can directly jump to results and takeaways, given we got a picture of how charts are selected and how questions are constructed and how answers are validated. So first of all the models struggle with reasoning questions. We see 20 points gap between the leading model and the human expert. And open source models, the highest one is, I think it's interval 276, but it's a 70B model based on llama. From there, we see that the vast majority of all models cannot even achieve a score above 30, which translates to that they incorrectly answer 70% of the reasoning questions. Note that the educated random guesses will incorrectly answer 90% of the questions as a reference. So it's not a lot higher than just randomly guessing.
Green are just open source.
Yeah, green are open weight actually. I just refer to open source here. Similar trends for descriptive questions, but the gap between the closed source models or proprietary models and humans are smaller. One interesting thing we see is that if you carefully check the above two slides, you can realize that the ranking pattern appears very similar. So with our post analysis after our preprint, we actually found something very interesting, where we found a 0.89 correlation between the performance of descriptive reasoning question when we fit a linear regression with this formula, 0.52 times your descriptive score minus 0.83, you will roughly get your reasoning score. This is very interesting, but it's also kind of intuitive because many models come up with zero-shot chain of thought. And if they make mistakes in any intermediate state, it's likely that they compound the mistake later and result in a wrong answer. This is especially true for reasoning questions. And another direct question out of this linear regression is that it seems that the reasoning score is the upper bounded at 51 points, assuming model achieves a 100% descriptive score. So we do believe that something is happening that can either bump or drag down the performance on reasoning questions holistically, that are other than the descriptive questions. And again, we also found that zero-shot chain of thought may not actually always be helpful. We see stronger model performance improves with more reasoning, while weaker model performance can actually degrade with more reasoning. So we conjecture that the perceptual errors made in the chain of thought can compound in the chain, which will lead to a wrong conclusion. And finally, we see some of the strongest models whose performance doesn't really vary by the length of reasoning for reasoning questions on targets such as GPT-4, which is on the top. Finally, I think we have 2 slides left. Our fine-grained analysis on descriptive questions, we found the vast majority of models fail to perform sufficiently above random chance, but the task itself is highly compositional and rarely appear in nature, right? So one specific descriptive question is to ask models to count the number of labeled ticks on both x and y axis. So like this, 1, 2, 3, 4, 5, etc. And we see about humans achieve like almost perfect score, which is kind of very intuitive, given how easy the task is. A lot of models cannot even get it right for even 10% of the time. On the other hand, we do see that there might be a scaling effect that larger models tend to do well on this task, or models that may have been distilled from larger models, totally by conjecture, such as GPT-4 Mini. I think that a Turing test based on this question will make humans models distinguishable by a lot if you compare their performance gap.
Do you know how robust this is? Like, I think how much of it depends on the prompt? Like, if you kind of into the model in the prompt.
That is a good question. We didn't do any ablations on that, but we might be able to find a pattern there.
Yeah, we're doing something similar.
Like prompt tuning or something.
Yeah, exactly.
Weak models failing to identify unanswerable questions. This is the first that we discovered because previous work they didn't, as if model rejects the answer if elements don't exist in the chart we showed in the example before. From this, I guess a possible direction would be to reduce like VLM hallucinations with a bunch of models and use their disagreement as a signal for potential hallucination reductions. But we'll just leave this as a future work. So you can see that different models make different types of mistakes in unanswerable questions. And lastly, pretty intuitive, we see that both reading descriptive questions degrade when there are more subplots and more pronounced for open source models. The reason that it's intuitive is because open source models, we know they're training data from their technical report, and we know that the data don't contain charts with multiple subplots. And unfortunately, the chart, they just all involve single plot. So from the plot itself, we see the models still fail. I mean, they still generalize to multiple subplots, but it's not a robust generalization. So there's still like this score, performance drop when there are more and more subplots involved in a single chart. And this happens for both open source and closed source models. Proprietary or closed source models are just more robust, I think, than open source models. So summarizing everything is my final takeaways. I think good evaluations need to be diverse, realistic, and curated by human if possible. So unlike chart QA, where the strongest model achieve like 90% plus accuracy, strongest model can only achieve 60% accuracy on Charkive. Second place only achieve like less than half. So Charkive revealed lots of shortcomings and insights of multimodal large language models in chart understanding, including that reasoning capability in chart highly correlates with descriptive capabilities. Multimodal zero-shot chain of thought can sometimes be harmful if there are a lot of perception issues.
Colin?
Yes, last.
Yeah, okay.
Okay, we can.
Maybe
Yeah.
quickly,
Yeah.
quickly wrap up.
Models struggle with questions that are very easy to humans. Models hallucinate on unanswerable questions in chart understanding. And finally, model capabilities degrade with number of subplots. And that is the end of my talk. Thank you.